Hello, welcome. Round 4 of our lockdown fall 2020 USN AP Chemistry videos. Probably the last one that we'll do on review topics. I may talk a little bit about the lab in another video, and then we'll kind of wrap up this unit and kind of move on to our next unit. So we're almost there. We're just flying on through. So this one is going to be on a classic sort of problem that is not really a major topic on the AP. It used to be. Now they're not quite as worried about it as they used to be. But it's certainly a very good technique, problem sort of solving idea to have, to understand, to be able to manipulate. Again, all sort of building that toolkit that helps you solve lots of other types of problems. So again, the concept here is relatively simple, and I don't know how you may have learned it in previous courses, but the idea really is that one of the ways that scientists used way back when to try to figure out what unknowns were before all the fancy equipment that we have now is simply you would take an organic compound, and most organic compounds burn pretty well. And most of them are made of C and H and usually O, sometimes S or N. And if you burn them, you make a lot of CO2 and a lot of water and occasionally a little bit of other stuff. And if you can capture the CO2 in the water, which as it turns out is not all that difficult, you can weigh the amounts of CO2 and water that you collected and compare that to the amount of substance that you burned, and you can actually figure out a whole lot about the substance's formula. So that's the idea of combustion analysis. Of course, the big downside of combustion analysis is that your sample is destroyed. It doesn't really come back, not certainly in any easy way. So once it's been destroyed, it's pretty hard to undo. So it is a rather catastrophic thing, but still a pretty good system of learning what a substance's formula was. So let's work through an example today. Let's say that we have 3 grams of an unknown organic compound, and the organic compound is burned in excess oxygen. The idea simply being that we have more than enough O2 to make sure the whole thing burns completely. If it burns incompletely, all this goes out the window and doesn't work very well. So 3 grams of the organic compound burned in excess oxygen, producing 7.33 grams of CO2 and, believe it or not, 3 grams of H2O. And so what we'd like to know is, what is the empirical formula? And so the empirical formula, remember, is the idea of the lowest ratio of everything in the compound, not necessarily the actual formula, but the lowest whole number ratio. Sometimes the lowest whole number ratio is the compound. Sometimes it's not. And so we'll look at that as we go through this problem. So lots of ways, again, to approach this problem. What I find to be the easiest is that I want to isolate the C in CO2 and the H in H2O. Because the substance was burned in oxygen, which is just O2, the presence of any C in CO2 or H in H2O came from the substance that we burned, because it couldn't possibly have come from the O2. So if we want to find the C in CO2, there's lots of ways to do that, but it actually goes back to the simple stoichiometry that we did a couple classes ago. And if I simply take the 7.33 grams of CO2 and multiply it by, well, there's 1 carbon, 12.01 grams of carbon, 1 mole's worth of carbon in every 1 mole of CO2. And CO2 weighs 44.01 grams per mole, carbon weighs 12.01. So what we're saying is that there's 1 carbon in every 1 CO2. Or if we scale it up as we have here, there's 1 mole of carbon in every 1 mole of CO2. So we do that, we get right around, if you do the math, right around 2 grams of carbon. And again, I encourage you to work through this with your calculator. Make sure that you're getting the answers I'm getting. Make sure you kind of ingrain what I might term, if this were athletics, some muscle memory, so that you kind of learn to do the motions. I don't know that anyone gets particularly good at shooting free throws simply by watching someone else shoot free throws. I don't know that I would become a good artist by watching Bob Ross paint happy trees. Like, you kind of need to do it yourself. So follow along, do this yourself, kind of get that practice ingrained a little bit deeper than just by watching a video. So we get 2 grams of carbon in doing that. And then we've got 3 grams of H2O, and we'll do the same thing. I want to find how much H there is in the H2O. And so unlike the carbon in CO2, there are 2 H's in H2O. So 2.016 grams of H in every 18.016 grams of H2O, or 2.02 and 18.02, doesn't really matter. And when you do that, you should get around 0.336 grams of H. Now, I will say this. The biggest place that people make mistakes in this type of problem is right here. They tend to forget that there are two H's in H2O, and once you do that, everything falls apart. Because you get the wrong mass of H, and that means you get the wrong ratio. You may also, if there's a third element, get the wrong mass of that element as a result, so the ratio is even further bungled, and things really go to pot pretty quickly. So make sure that you have that sort of set in your mind that it's 2.016 over 18.016 or 2.02 over 18.02. Now, I very much in the College Board, when it asks these kinds of problems, is sort of the same way. I don't like to tell you whether it has O in it or not. It could just have C and H, it might not. Now in this case, I hope by thinking about that briefly, you can tell it has something else in it because the compound weighed 3 grams, and these two together do not add up to 3. So there is another element present in here, and for the problems that we're going to do, unless told otherwise, the other element should be oxygen. So the O that's in this compound is going to be equal to the 3 grams that we started with minus 2 grams of carbon minus 0.336 grams of H. That should be about 0.664 grams of O. And so now we have masses of the 3 elements that we need, the C, the H, and the O. And so the next step is to convert them all to moles, because the best way to find a formula is to compare mole ratios. So we divide each by its molar mass. 12.01 for carbon, 1.008 for hydrogen, and 16 for oxygen. So 2 divided by 12, 0.336 divided by 1.008, and 0.664 divided by 16. And when you do that, you get 0.1665 moles of C, 0.333 moles of H, and 0.0415 of O. The next step, if you remember your little rhyme, mass to mole, divide by small, multiply till whole. If we divide by small, or small, the smallest number of moles is this 0.0415, so we'll divide all of these by 0.0415. So I'll just write that a little larger. And that should give me a number of moles that hopefully is pretty close to a whole number. And I'm running out of room, but imagine I did that more cleanly here, and I would get 4 C's, 8 H's, and of course 1 O because we divided it by itself. So our empirical formula is C4H8O. And that would be as far as we could get under most circumstances. And then the question might be, well, is that the actual formula or just the molecular? There's no way to tell at this point. What you would need is some other evidence. Primarily what you would need is the molar mass. And so if I had the molar mass, then I could figure this out. Let's say the molar mass is 144 grams per mole. All I have to do then is compare, and before I get ahead of myself, that information can come from lots of places. So we've talked about techniques, at least I know I did in Chem 2. One of the ways might be you convert it to a gas and use the formula for Pivnert to figure out how many moles there are when it occupies a certain amount of space at a certain pressure and temperature, and that helps you find molar mass using the somewhat famous dirty P formula, density times RT over pressure. You could use it with dissolved liquids because liquids lower the freezing point or raise the boiling point according to their number of moles, which helps you find molar mass as well. So there's a variety of ways that you can kind of find molar mass. But let's say we were sort of magically given this value and it's 144 grams per mole. What we would do is we'd find out how much does C4H8O weigh. And if you do that, it weighs right around 72 grams per mole. The real thing weighs 144. So if I do 144 divided by 72, I get 2. If you're doing one of these problems and you don't get something really close to a whole number, like you get like 1.73, that's not a good sign. It's very likely that you've made a mistake. It is certainly possible, as I admitted to earlier, that I'm human and I make mistakes. It is certainly more likely in the context, if I've given it as a test problem, that you've made a mistake, that we've uncovered it. So again, some number sense, some awareness of the fact you're not getting something really close to a whole number. No, like if you get 2.02, you're probably okay. There's a of course, chance that you're not, but the chances are better that you're okay with 2.02 than you are with 1.73. So hopefully all has gone well if you've gotten something really close to a whole number. So if that's 2, I go back and just double everything. And there, and I would get C8H16O2. And that would be our compound. All right, so a little refresher on combustion analysis. Again, hopefully based on the previous video, you're starting to think of a good catchphrase that I can say to close out our videos. Hopefully they'll be implemented soon. I'm recording these before school starts, so it's hard for me to respond to them. So have yourselves a wonderful afternoon or evening, and I will see you virtually again quite soon.